My dear students of CE806, Structural Analysis and Design of Concrete Structures 2 Sessional. This is the bridge part, lesson 2. In the previous lecture, we have shown the long section of the bridge and we had some calculations like the diaphragms. The diaphragms are the cross beams. At the support, the diaphragm is equal to the depth of the beam, and in the intermediate position, the diaphragms are less than the 1 foot less than the depth of the beam. And from there, we had some third page down, page. Here, this is a long section of the bridge drawn, and we have marked this bridge by number, given different number of the locations. And the locations we have started from the center of the bridge at the middle of the bridge. We have noted the center of the bridge or the middle of the bridge as 1, and as the cantilever span was 30 feet and the other spans are 90 feet, anchor span is 90 feet, the cantilever is 30 feet, and on the cantilever there is a 60 feet suspended span, 60 foot suspended span, and this 60 foot suspended span, center of the 60 foot suspended span is named as number 1, and the leftwise towards the end of the bridge we have given the 8 30 feet, there is a number 2, and number 3 is the central support, and there is a number 4, 5, and it ends at number 6 in the end support. So now from now on we will be calculating moment, shear, reinforcement, all these on these points 1, 2, 3, 4, 5, 6 points. These are 30 feet apart, but in real case when you will be designing a real bridge for construction, at that stage you will be taking 10 foot gaps, and there will be many numbers for calculation and changing the reinforcement, changing the depth of the beam. Here, as we are just practicing a bridge, that's why we have taken these gaps a little more than the standard one for minimizing the calculation. That's all. And therefore, I have from now on we will be noting the positions, and for the positions 1, 2, 3, 4, 5, 6, we will be calculating values for moment, shear, reinforcement, all these things. We will not touch the other points. And the dead load was previously calculated, and the uniformly distributed load is 2.38 kip, and the diaphragms were, for the intermediate diaphragms, the loads were 3.6, and for the support diaphragm there is 2 different types of load. One is the left support, the diaphragm load is 7.9, and the intermediate support, the diaphragm load is 12.5, and now on we will be designing the beam, we will be noting the beam from point 1 like that, and at point 1 there is a reaction of the intermediate suspended span of 60 feet. There is a reaction at the point 1 is 80.6 kip, 80.6 kip. For the 60 feet bridge, the dead load is 77, and the diaphragm load at that point is 3.6 added. That's why the load on the cantilever part of this cantilever part of the anchor span or the left span is 80.6 kip, 80.6 kip, and the uniformly distributed load is, again I am telling you, this is 2.38 kip. The diaphragm at the interior support is 12.5, and the diaphragm at the exterior support is 7.9, and diaphragms at the intermediate position are 3.6. This is the load with which we will be dealing with next on so far the dead load is concerned. Page कौन पृष्ठ है? Page 4A6. ठीक है. We have shown the diaphragm weights, load from slab to beam, and wearing course, etc. All this is, and the load per safety is per running foot of the beam is 2.38 in this page number 3. You will follow the calculation number. Weight of the slab, slab thickness is 7 inch minimum, and per inch thickness of slab weighs 12.5 pound. That's why it is 7.5 here on page 3. And wearing course we have used 30 pounds as you have done in the previous course. That's why load per safety is 87.5 plus 30 is 15. And all these simple calculation is very it's easy, you can follow as you have designs slabs in the other courses. That's why the per square foot load is 0.98, and the total dead load is 1.4 plus 0.98 is 2.38 kip per feet. Per is 2.38 for the the reaction reaction calculation at different locations of the bridge. If you take moment about R6 left support, then there are many loads there. You have to check it and try to understand it. It is so the line is very long, but if you go carefully, then you will be able to understand that. First of all, we have multiplied this 2.38 kip, which is the distributed load all through the bridge, and that is multiplied by 120 because left span is 90 and cantilever span is 30. That much. And this part we will be designing for this course from 0.6 to 0.1. 1 and 2 is the simplest supported beam span, and we will actually start from 0.2, 0.3, location 4, 5 and 6. These are the 6 points we will be dealing in this other lectures, following lectures. Here you have to understand that 80.6 is at the center, at the cantilever, tip of the cantilever. This 0.2 shows a load of 80.5. The 77 pound is the load from the simply supported span of 60 feet, and from there we got a load of 77, and at the tip of the simply supported span or the cantilever span, there is a diaphragm. The diaphragm weighs 3.6 kip. We have shown somewhere that the weight of the weight of diaphragm has come as 3.6 kip. That's why 77 plus 3.6 kip is 80 kip. 80.6 kip is the load at the tip of the cantilever. And 2.38 is the distributed load from the slab, and 3.6 is again there are two intermediate diaphragms and two support diaphragms. As we have said, these diaphragms are cross beams, and at the support the depth of the diaphragm is equal to the depth of the beam, and intermediate the depth of the diaphragm is kept 1 feet less than the main beam. And we have shown that these calculations that the diaphragms are 7.9, 3.6, 3.6 and 12.5, and uniformly distributed load is 2.38 kip per feet. And if we take moment about 0.6, that's left support, then 2.38 is the first. The 7.9 will not produce any moment. 2.38 per running foot is the load, and our span in this case for which we will be working is 120 feet. The exterior span is 90 feet and the cantilever part is 30 feet, and total is 120 feet. First of all, we will take the moment about at 6, that the left support. The distributed load is 2.38 kip, and the distributed load from 120 feet will be first of all taken as a single load for taking moment about the left support. This is 2.38 into 120 into moment arm of that 120 feet spanner is 60 feet, plus next to 3.6 into 30 is the next load moment, and 3.6 into 60 is the next load moment, and 12.5 into 90 is the next load moment, and 80.6 is the into 120 is the final moment, and minus R2 into 90. 90 has gone to the other line. You must note it. The R3 into 90. 90 is on the left hand side of this line. Therefore, R90 is equal to the arithmetic calculation is shown here. You can check it and you can understand this. These are the all simple arithmetic calculation, and after the arithmetic calculation we have got R3 is equal to 314 kip, and R6 just by adding and deducting the loads, total loads and the reactions etc., we get the reaction at 6 is equal to 70.2. If you see this page again, there are several loads and the distributed load. Now our aim is to find out the bending moment and shear force diagram for the 120 feet span. Out of this 120 feet, 90 feet is the support to support span, and 30 feet is the cantilever. And the reaction at the two supports, we have got this reaction. One is 70.2 and another is 314 kip. Okay, next page. Now we have brought those reactions and the moment shear diagram. First of all, we will draw the shear diagram, and then from the shear diagram we will draw the moment diagram. On the left hand side, the shear diagram below is the reaction is 7.2, but just the beam shear will be the 70.2 minus 7.9, because 7.9 will be directly on the support. That's why the shear that the beam will be 62.3 at this point. And if we divide the 62.3 by 2.38, then at a distance of 26.2, the shear is 0, and the shear at the next change point, we will be always referring this change point, and we will work on this change point only, and we will find out the moment, shear, section, etc. on these change points 1, 2, 3, 4, 5, 6, and for the left support is 0.6, and the next point is 0.5. At the 0.5, the distributed load minus this slope of the distributed load cuts at 9 kip in the 5 point line, and there is a concentrated load of 3.6, and 9 plus 3.6 is 12.6, and again we will go to we will find out the value at the next point, or the 0.4, and there 0.4, there will be another 2.38 multiplied by 30 is a value, and that plus 12.6 gives us 84 kip, and with this 84 kip we have to add 3.6, and that will give 87.6 kip. And next, if we go ahead, if we add with 87.6 the value for this 30 feet value, then it comes as 159, and this is the shear, left shear of the support. And if we come from the right side of this beam, at the tip of the cantilever, the load is 80.4, and that is the shear at that point. And with this shear, if we add 2.38 into 30, and if you add it, that gives you 152 kip. And this is the shear diagram. Right hand side we have a concentrated load of 80.4, and the distributed load on this cantilever span is 2.38 multiplied by this 30 plus 80.4 is the shear. On the right hand side is 152, and on the left hand side we have got a shear of 1.59, and this 12.5 will not come into the shear, it will come to the reaction of the beam, reaction at the beam for designing bearing etc. of this bridge. This 12.5 will not come to this shear value, and that's the shear diagram. On the right, if you come from right hand side, is 80.4 is the concentrated load coming from the suspended, simply supported suspended span, and with this we add 2.38 into 30, that gives us 152, and if we come from the left hand side, the reaction is 72.2 and minus 7.9 is 62.3, and with this, if we add some value, if we want to find out the zero shear point, then we have to divide the 62.3 by 2.38, and that gives us a distance of 26.2, and this is the zero shear point. And with this 26.2, if we deduct this 26.2 from 30, that gives us some 3 point something, and if we multiply that by 2.38, then gives us a value of 9, and there is a concentrated loss of 3.6. Added this 3.6 gives us 12.6 as the shear at that point. And with this, if we go on adding 2.38 into 30, that gives us 87.6 as a point, 84 as a point, and there also is a concentrated load 3.6, 84 plus 3.6 is 87.6, and the other hand of the right hand side is calculated from the right side of this beam. Now we have to find out the moment values, and moment values are the where from, if we start from right hand side, the figure, this rectangle has a side of 30 feet, and the horizontal side is 30 feet, and the two vertical sides are 84.4 and 152. If we average these 2 points and multiply by this 30, then you will get 3486 as the moment of the support. And if we come calculate moment from the left hand side, then the first angle is 62.3 the height, and 26.2 is the base, half base into altitude is we'll be getting a moment, and from that moment we have to deduct the smaller triangle which has a side of 9 kip height and only small amount of area, and if we deduct this small area, that gives at the point 5 the moment of 795 kip feet. And with this one, if we add the area of the center figure, the height of this figure is 12.6 and the another height is 84 kip and the length is 30 kip. If we make 12.6 plus 84 kip and average it and multiply it by 30, that will give us a value, and that value minus this. From 795 we have to deduct that value, and that will give you a value of 644. There is 654, that value is. Said that the value is 3486 kip feet, and this is the diagram of the bending moment and shear force diagram. And with these values, this is for the dead load, and we will next go for the live load. As you, in the previous case of the simply supported bridge of 60 feet, we have done in the similar way. That was a simple structure, and here it is a cantilever part. There is a cantilever part. Okay. Thank you.